So our next speaker is Nikki Miller from Keele University. She's a PhD student there, as far as I know, and working on a new method to determine the temperatures of stars in eclipsing binaries. As much as I could understand, also, please correct me if I'm wrong, she is also an active science communicator, doing very nice talks, and also involved with the International Astronomical Youth Academy, Youth Camp, sorry. So she'll be today talking about high precision fundamental effective temperature measurements for cool stars. Nikki, thank you very much for the contribution, and we are listening to you. Thanks.
Thank you very much. I'm very glad to be here and talking about my research. So if it would be possible to share my screen. Oh, there it is. Perfect. Okay, can you see this okay?
Yeah, perfect.
Fantastic. So my research during my PhD has been on the subject of measuring the temperatures of stars and eclipsing binaries. So I'm going to take you through sort of the motivation for this research, what we've developed so far, and the targets that we've applied the method to, and finally summarize kind of what we've learned so far and what I hope to do with the method in the future. So first of all, why do we actually care about the effective temperature of stars? Why do we care about the temperatures of FGK type stars? So first of all, just a reminder, the effective temperature for a star is defined by the Stefan-Boltzmann law, which I'm sure you're all familiar with, which can be rewritten in this way to make temperature of the subject in terms of observables, so the angular diameter of the star and the bolometric flux. Any other sort of temperature estimate is an estimate. The only direct way to measure the temperature is using this definition. So FGK type stars are some of the most common stars that have exoplanets. They're discovered around them. So of course, if we want to better understand the exoplanets, we need to understand their stars. So an important group of stars to look at, of course, would be the FGK type stars, as you can see in this histogram on the left. In addition, a majority of stars near the sun in the local stellar neighborhood are FGK type as well. So in the plot on the right, I've got the temperature against the luminosity for stars in the GCS catalog. And the ones that are in blue are the stars with age estimates that are better than 10%. So if we can get stars that are very well characterized in that region, that will really, really help pin down stellar models, particularly in that part of the evolution. So we need, why temperature specifically? Well, most stellar temperatures for FGK type stars are actually only accurate to about plus or minus 200 Kelvin, best of which being about 50 Kelvin. This is discussed in this review paper by Joffrey et al. And you know, even direct temperature measurements for these types of stars carry quite a large systematic uncertainty, which is up to 100 and 120 Kelvin for a solar type star. So this is an issue because uncertainties of even 75 Kelvin in the effective temperature can lead to an underestimation of the derived ages of stars. And any kind of systematic error in the temperature that can lead to spurious trends if you're doing large scale spectroscopic surveys, for example. So this plot I have here on the right shows the systematic error in temperature and how that has an effect on the derived age. On the y-axis, we also have the metallicity. As you can see, as we increase the systematic shift in a set of temperatures, we do start to get an offset in the age, which is definitely a problem. So what we need is a set of benchmark stars with accurate and precise effective temperatures that we can trust. We need them to calibrate stellar models. We need them to help, sort of calibrate and test pipelines, machine learning methods, all kinds of things that we're doing in modern astrophysics. So one example of this is the upcoming Plato mission. This is an ESA mission that's going up in about 2026. And the goal of the mission is to search for Earth-like planets around sun-like stars. And to do that, they've specified a requirement on a 10% uncertainty in stellar ages. So the current generation of stellar models absolutely need some work before we can reach that 10% reliably. So for that, we need a set of benchmark stars. So my work feeds into the benchmark stars package for the Plato mission. So the current status of FGK type benchmark stars, we have the Gaia FGK benchmarks, which you might be familiar with. These have direct temperatures measured where the angular diameters come from interferometry, and the bolometric flux is simply taken as the SED fitting. Unfortunately, for interferometry, the sample that you can get of stars is fundamentally limited by the distance and the size of the stars. So there's only a handful here that you can see on this temperature log-G plane. By that nature, they're also very bright. So if you want to have a calibrator in your spectroscopic survey and you're looking at much fainter stars, interferometry benchmarks are a bit too bright and you need to sort of use a different mode, for example. And even so, the systematic errors on the angular diameter for interferometry is still in the range of 3 to 5% due to uncertainties in the limb darkening. So we have some benchmarks, but they're not perfect and they're a little bit limited. For example, we would really like some more F-type stars, some more metal poor stars. So this plot here I've got on the right, you'll see a few versions of this as I go through my talk. And this shows again the GCS sample as the hexagons as a sort of density plot. On top we have the Gaia benchmarks in purple, and we also have the Kepler legacy sample. So these are stars where they have detailed astroseismology. So if we want to, for example, test astroseismology scaling relations, it would be very useful to have more benchmarks in that regime as well. So detached eclipsing binaries, which I'll sort of explain more in a minute, they have direct masses and radii and have the potential to be really, really powerful benchmark stars. As you can see, they're already starting to fill a lot of the space the Gaia FGK benchmarks haven't been able to fill. But the thing holding us back is the temperature. As you can see with the uncertainties in log-G, you can barely see the error bars for these stars, but for temperature, they're a lot bigger. So this is definitely something that's worth looking at. So what's so great about detached eclipsing binary stars? So when I say a detached eclipsing binary, I mean an eclipsing binary system where the two components can be considered like single stars. So they have not gone through mass transfer, they're not tidally locked, for example. This means that we can compare them to single stars for the purposes of testing stellar models. The fantastic thing about eclipsing binaries is that we can assume that they're at the same distance, the same age, the same composition. So if you have two stars in an eclipsing binary at different evolutionary stages, you can really, really test your stellar models. For our purposes, we prefer to have quiet and clean systems. So we prefer to have no, ideally, star spots. We prefer them to be slightly slower rotating. So when we derive the radial velocities, there's less line blending. We prefer to have stars with total or near total eclipses. This removes some of the model dependence in the derived parameters. And as I said before, we prefer not to have them tightly locked because you wouldn't get that in a single star. So eclipsing binaries, by the name, they have eclipses. So this is kind of a quick diagram of what we kind of see. So you have usually have a primary and a secondary eclipse if you have two FGK type stars. And this light curve down the bottom, this is real test data with a model on it. This is how precise photometry is getting these days, which is really, really exciting. You see here we've got a deeper primary eclipse and a secondary eclipse with a very distinctive flat bottom. This means that we know for sure that it is a total eclipse, which is actually quite powerful. I'll talk a little bit about that at the end. By their nature, eclipsing binaries are also spectroscopic binaries. So if you have one component moving towards you, you get some shift to the blue and shift to the red if they're moving away, for example. So we measure the radial velocities for eclipsing binaries, and we can derive a spectroscopic orbit. So by combining the analysis of the light curve and the spectroscopic orbit, we can get really, really fantastic direct measurements of the mass and radius. So the current state of the art catalog of eclipsing binaries is DEBCat, hosted by John Taylor at Keele. And as of last week, there are 289 binary systems in this catalog with masses and radii measured to better than 2% uncertainty. So that's 289 systems, so that's twice as many stars. So with TESS and modern Echelle spectroscopy, we can actually get better than that. And we're routinely finding these days that we can get better than 0.5, 0.2% uncertainty on the mass and radius of stars in detached eclipsing binaries. All of the components in DEBCat have an effective temperature estimate, but they all use different scales, they all use different definitions, so it's completely inhomogeneous and we can't use it for any kind of population studies or anything. And again, the metallicity estimates in this catalog are a little bit sparse and they use different definitions as well. So here on the right, we've got, just to sort of demonstrate how fantastic these mass and radius measurements are. These are not plotting symbols, these are the error bars on the points themselves. So it's a really fantastic catalog and it's growing day by day. So our new method for measuring the effective temperatures of stars and eclipsing binaries. So our method is based on the Stefan-Boltzmann law. As I said at the beginning, this is the only way that you can get direct effective temperature. When you have two stars involved, it does get a little bit more complicated. So we consider the total flux for the system is a combination of the flux from the primary star and the secondary star. In order to determine that for both stars in an eclipsing binary, well, we can't just take some photometry and construct an SED. We need to understand how much light in each wavelength comes from each star. So we need to have as many flux ratio measurements as we can. So a flux ratio measurement is taken using a light curve. So that sort of, it comes from when there's a total eclipse, for example, it's most easy to do this. You can determine how much flux comes from each component. So we need as many of these measurements as we can throughout the optical range. We do also need to consider the interstellar reddening because we are dealing with photometry here. And we do have an additional uncertainty that comes from the Kelzberg flux scale that we can't avoid. Again, so for the angular diameters, this is a lot simpler for eclipsing binaries. We simply just need a measurement of the radius for both stars. And this is known to better than 0.5% for the stars that we're looking at. And the parallax as well. This comes from Gaia EDR3 at the moment, but this is only going to improve with subsequent data releases. So the bolometric flux, I think, is actually the trickier part of the method. So we need to include the photometry, so as much photometric data as we can get on the system. So photometry through an eclipse gets us the light ratios. Catalog photometry throughout UV, visible, infrared, as much as we can. Colors as well help us pin down the shape of the flux distribution. But we also want to use model SEDs to get those small scale spectral features properly included in our analysis. So for our method, we're using the BT-settle models, but I've tried lots of different variants of these models, and we do have a way to get rid of the model dependence. So here I've got on the right is kind of a representative collection of the photometry that we use in the temperature method. So we have the model fluxes at the top for the two different stars. We have the magnitudes all the way across, and we have flux ratios. So for this particular system, we have a huge number of flux ratios, but this isn't usually the case. For the reddening, we use a direct measurement using the sodium D1 line, which there's lots of different ways that you can estimate the reddening. We prefer to use the direct method, but I can talk about that a little bit in a minute as well. So to remove this model dependence, what we do is we assume that the true SED is constructed of this model multiplied by some distortion. So we use Legendre polynomials, and we use them to distort the models to fit the photometry data. And we normalize them as well. So these integrating functions that we get at the end of the method are not simply just fitting the best model to the data. We're actually changing the models. So this removes some of the model dependence, and it's not the same as regular SED fitting. We've tried doing the SED fitting, and that's actually a huge underestimation of the errors. This little animation here kind of shows what's going on as the fit takes place. So bringing all of this together, we have the model parameters, including some extra error on the magnitudes, flux ratios, and colors in case they're not perfect. For the data as well, we have our angular diameters, magnitudes, flux ratios, colors as well. And of course, we do need to have some metadata there as well. So the photometric response functions, the 0 points, which we've had to sort of independently check to make sure that everything's working correctly. We bring all of this together and we use MCMC to sample the posterior distribution, and that finds us the best solution for our system. So how does this look when we actually start applying it to different systems? So first of all, AIFE is a very well studied F+K binary, and it's a detached system. All of these are. It's totally eclipsing, and it has a 24-day orbital period. You can see its test light curve on the right. It's such good quality data that the residual of the fit has been multiplied by 10, so you can actually see it. AIFE has been the subject of a number of studies through the last 50+ years. So there's huge quality, a huge wealth of quality light curves, all the way from the ultraviolet through to the infrared, which is pretty cool. The radii were measured by my supervisor Pierre Maxted in his paper, and these were measured to better than 0.2%. We also have an independent parallax measurement for this system, which is quite unusual, but it means that we have a much better understanding of this system. So ultraviolet light curve is not something you usually hear. And for this system, we were very lucky to find that the IUE satellite back in the 1980s had taken 7 or 8 spectra in the ultraviolet of AIFE during a total eclipse and as it left total eclipse. So we were able to use these spectra and do some synthetic photometry to generate a light curve, and then fit that light curve to get a flux ratio. So this is a really, really powerful thing, because otherwise we wouldn't have been able to pin down the flux so well in the ultraviolet. So our result here is what the still version of that distortion plot that I showed you just before. This is the best solution for the system, and also the corner plot showing all of the free parameters that we had going through the fit. And as you'd kind of expect, the temperatures are a little bit correlated, but there's nothing unusual going on. And we land on these results. So our temperatures are plus minus 22, plus minus 16. And this is significantly better than anything before. We published our results in my paper back in 2020, and it's a really promising system. And we're very glad to have studied this one as the first one, because it shows you just how powerful the method can be. So the next system that we studied has taken significantly longer, actually, because it doesn't have nearly as much good data. So CBD minus 54 at 10 is a recently discovered or recently characterized ASAS binary. The two components are actually quite similar, and we have a test light curve, but that was it. The ASAS and the WASP light curves that we had were not very good quality, so we had to go and obtain some additional light curves, which did add to sort of the time it takes to analyze the system. But this is quite representative of a standard system, for example, discovered by TESS, which only has a TESS light curve. So we've been able to figure out what we need and what we don't need using this system. So here we have the TESS light curve of this system, along with the fit that I've done. As you can see, it looks very clean, very exceptional. The actual spread and the residuals, this is actually a preliminary fit. I've had to go back and reanalyze, re-extract the TESS light curves, because there was a slight discrepancy in the pipeline generated light curve. So we expect these residuals to actually shrink a bit and the results to improve a little bit by the time it's published. So this system's definitely more of a challenge, because we've got two stars of very similar types, much fewer data available. So as I said, we had to go and obtain some extra light curves. So using the Perth Exoplanet Survey Telescope, we've got an additional 4 light curves. This is all we really need if we have a total eclipse. Just some photometry during totality, and then at the out of eclipse level. And we're able to fit the model and get some additional flux ratios. So this is sort of the distortion plot for this system. As you notice, it's a lot less sort of noisy in the distortion panels, and that's because we used fewer coefficients, because we had less data. With ARFE, we had so much data, we were quite justified in putting a higher order distortion polynomial, but here we have to put fewer because we don't have so much data. So in the visible range, we're very well pinned down, and in the infrared range, we actually use some priors, because the flux of the infrared is pretty well understood. So I can talk about that a little bit at the end if you're interested on how we put some priors on the infrared flux, just so the distortion didn't go absolutely wild down that end. So our results for the system, we have got a 0.1% uncertainty on the radius, which we're really happy with. So we completely reanalyzed this system, following on from the paper by Radshak et al. And we found the temperatures to be actually significantly hotter than their temperatures. So in this paper by Radshak et al, they used the spectroscopy to find the temperature, whereas with our method, sort of based more in photometry, we get a much hotter temperature, which is quite interesting. We also really slimmed down those error bars. So we're pretty sure that that's where the temperature is, and that the result based in spectroscopy is due to the quality of the spectrum. So we did some quick evolutionary modeling on the system as well, and we find some really well constrained results for our analysis compared to the previous analysis, which is the red, the gray. So the primary system is just off the blue hook. So it's fantastic benchmark stars for sort of pinning down that part of stellar evolution. So finally, we have one more system that we have looked at. So this work was led more by my supervisor, but I contributed with the temperature method. So EBLM, that's a low mass eclipsing binary, where you have one component that is sort of GF type with a much fainter M type companion. This is quite interesting because you can look in the visible region and you just see the single star as if it's a single star. But then if you use near infrared spectroscopy, you can turn it into a double line spectroscopic binary. And if you look in the infrared as well with the light curves, you can also get that tiny secondary eclipse. So you get all the benefits of an eclipsing binary without having to worry about the contribution to the flux in the visible range from the M dwarf. So you can look, for example, you can take a spectrum of the system, and the contribution from the M dwarf is so small that you can do an analysis on the system as if it is a single star. So these are really potentially powerful systems. So my supervisor led this work on EBLM 0113, and he obtained a light curve of the system with the KOPS satellite as well as the test satellite. You can see the improvements on the photometry with the KOPS satellite and the light curve on the right. He also worked on getting a good estimate on the mass and the radius using these light curves as well as near infrared spectroscopy. And then also got the temperature using the method that I've described during my talk. And this is the final sort of flux integrating function for the combined system. Contribution from the M dwarf is so small, you can hardly see it in this. So the results for this system are really quite good. And they're published in a preprint at the moment, led by my supervisor. So we've found ourselves another G-type benchmark, which is really great. So when we bring it all together, you can see that we're starting to populate this temperature log G space quite a lot. So the two yellow points where you just can't see the error bars, that's AIFE, the first system that we analyzed. The two ones towards the left, that's the CPD system. And then again, we have this G-type star, which sort of sits in the middle. So all of this work is really great. And it just goes to show that eclipsing binaries are definitely going to help fill out this space and create a benchmark sample. So what have we learned so far from this method? Well, in terms of distortion, as I kind of briefly said before, the number of coefficients, i.e. the order of the polynomial that we use to do the distortion, that should reflect the amount of data that we have available. Otherwise, you'll be overfitting. So for AIFE, we're quite justified in using a larger number, whereas for the other two systems, we use a smaller number, and we still achieve pretty good results. Changing the number of coefficients doesn't actually change the numerical value of the result so much. It just increases the error slightly because we're starting to overfit. In terms of the choice of the model, SED, we were concerned about the model dependence that we would be introducing. So we decided to vary the input models just to test, if we give it the wrong answer, can it still find its way back to the right answer? And we found yes, it can. So if we vary the input temperatures here on the left, also if we change the metallicity, we still land upon the same or very similar temperatures as the result. So that's very reassuring. When you're significantly too far off, so when we use the initial temperatures from the Bratislava paper for this CPD system, those were 500 Kelvin too cool. And when you're that far off, it starts to get a bit tricky. But as long as you're within 200 Kelvin, the code will still find you the right answer. In terms of reddening, well, so far the systems that we've looked at have been quite nearby, so they've only had a small reddening. So by changing the way that we estimate the reddening, so whether we use a direct method or whether we use reddening maps, it doesn't have a huge effect on the result that we get. It just increases or reduces the error bars. So the approach that we use, I sort of brushed over this briefly. We use a direct approach where we measure the equivalent width of the sodium D1 line. And as you can see for these two examples that I've given of the spectra, you can barely see the interstellar sodium D line. So we're definitely down this end of this plot of reddening against equivalent width. This end of the plot is a little bit sparse, so we would like to actually work on populating that a bit more in the future so we have a better estimate. In terms of the data that we need to approach this plus or minus 50K limit that we've put on ourselves, well, we need total eclipses, we need test light curves and a couple of others, depending on the quality. We do need an estimate of the UV flux, even if it's just a Galax photometry measurement. And we do need the radii to be measured very well, along with having a high quality parallax, which from Gaia is not a problem. So, this is the ideal scenario where we have flux ratios across the majority of where the flux is, but that's not always going to be the case. This flux scale uncertainty does place an extra 10 Kelvin or so on our estimates of temperature because there is an uncertainty in the flux scale 0 point. This is unavoidable, unfortunately, but it is a systematic error that affects all stars in the same way. So this plot here is just sort of showing what the error is throughout the optical range. So in the future, we want to look at more systems. We want to look at more systems with different metallicities. Everything we've looked at so far has been kind of solar. Fill out this log-G effective temperature plane. How extreme can we go? How hot can we go? How metal poor, how metal rich can we go? For example, can we measure giants, or are we just stuck with main sequence and subgiants? I want to address these observational bottlenecks that we have. So I applied for Swift time to get some ultraviolet photometry of an additional 6 systems that didn't have anything in that range. So I'll be analysing those next as those observations come in, and also applying for multi-band light curves until the Sami Demura instrument is ready. So that's this observatory that I've got as the background of my slide. This is sort of the evolution of the WASP instrument, where we plan to obtain photometry of just eclipsing binary stars, so a much more targeted survey in a range of bands. Unfortunately, it's not working at the moment, so I've had to look elsewhere for my data sources. And as I said way back at the beginning, with these total eclipses, they're actually very powerful, because when you're just looking at one star, if the total eclipse duration is long enough, you can actually take a spectrum during the total eclipse of just one of the components, and you can get a beautiful benchmark spectrum of the star, of one of the components of the star. So we did this for AIP. We have a UVES spectrum that's currently being worked on of just one component of AIP. And as you saw, the radii, the temperatures, the masses for that system are exceptional. So this will be a really, really stringent test for a spectroscopic analysis. So just to summarize, during my PhD, we've developed this new method that measures accurate and precise effective temperatures for FGK type stars. We've got some initial results for AIP, CPD, which is hopefully going to be submitted very soon, and this EBLM system. And we've got loads more binaries to look at in the future. So I've put on the ones that we just got Swift time for. So these stars, hopefully, I'll be able to analyze in the next couple of years. So yeah, the future is quite promising for this method. And I'm looking forward to being able to construct a homogeneous sample of stars with very good masses, radii, and temperatures. So thank you for listening.
Thank you very much, Nikki. Very good, very nice talk. Let me ask first if there are any questions or any comments, suggestions. I want to ask one thing, if not, first of all, you talked about the reddening uncertainties. You already kind of mentioned, but how much does it add to the temperature uncertainty, or how sure you are when you use or find one EB minus V value for a system? Like in the table you showed, there were uncertainties almost as big as the EB minus V values, if I wasn't looking at the something wrong.
So is this the table with the long table?
Yes, a few slides ago, actually, yes.
Yeah, I can show you the full version of this table, actually, here. So with the reddening, so this is the reddening for this system CPD, and this is sort of where the code lands upon it, which is kind of similar to the input that we give it. When we remove any kind of restriction on what the reddening is, again, the uncertainty is almost as big as the value. So we know that, empirically, just looking at that sodium D1 line, we would expect there to be a significant line there if there was significant reddening, and there isn't. So, yeah, it does have an impact if we don't constrain it at all. By using either a direct measurement, or we've used a couple of different reddening maps to pin it down.
You also said that you're kind of in the low reddening regime at the moment, like for the candidates you selected. What is the upper limit on that? Like, how far away will you be able to, let's say, continue while being sure that the reddening value you use or find is actually kind of secure?
Yeah,
there's kind of limit on that.
That's a question that I would like to investigate, actually.
Good.
Yeah.
Sounds. And one more final thing, if you don't mind. How many more systems I mean, like TESS observes all the days these things. So you said that there was this catalog of about 200 something stars, if I wasn't wrong. So how many of them are being observed with TESS, or I mean, how much observation do you need more, for example?
So TESS is observing pretty much everything. The bottleneck really is getting a second observation, or a third observation, using a sort of different band. So TESS is quite a wide band, which is great. But ideally, we would like, for example, BVR, or just a second space-based light curve. So with TESS, there have been literally millions of eclipsing binaries discovered. Another bottleneck for that, of course, is getting good quality radial velocities. So you can have billions of fantastic light curves, but if you don't have any spectroscopic information, you're a little bit stuck there. So there are loads of systems, but there are a few bottlenecks that we need to address. So I'm hoping that, now that we've sort of got the method really well understood, and we understand exactly what we need, I'll be able to sort of ramp up my analysis of these systems within the next 5 years. So
do you need, for example, multicolor ground-based observations of these systems, and like simultaneously in a few bands, or like?
Yes, ideally.
All right.
We found with the EBLM system that we could get by with TESS plus chaos.
Yes.
They're both quite wide bands, but for CPD, actually, if I get back to that table, without the PEST information, we do start to blow up the error in the temperature. So yeah, it is quite important to get those, but we don't need big fancy telescopes for this. You know, the Perth exoplanet survey telescope is just a single telescope in somebody's backyard. So it's very, very possible to get this information for the systems we're looking at, because we're not looking at anything too faint at the moment.
I see. Okay, cool. So let me ask one more time if there are any other questions in the audience, or if not, I'm going to thank Nikki one more time for this very nice study and very good talk. Thank you very much, Nikki, for contribution, and hoping to see more nice results. I mean, they are so precise that, you know, it's hard to believe to some degree. Very nice.
Yeah, thank you.
All right. Thank you very much, everyone.
Thank you, Nikki.